Good morning, everybody. Welcome to Pulsar Summit 2023. My name is Chandra Ganguly. I'm the Senior Director for Engineering at Cisco's IoT Control Center. Today with me is my colleague and the Principal Engineer, Alec Houghton. Both of us will talk about how we have taken Pulsar from working with StreamNative team and into our IoT Control Center. So what I will do is I'll give you a brief background of what Cisco's IoT Control Center is all about, and Alec will dive deep into how we've taken Pulsar and then included into a brownfield cloud and SaaS offering, and explain some of the challenges as well as where we are in this journey. So what exactly is Cisco's IoT Control Center? It really is device lifecycle management of any IoT device. So what are IoT devices? It can be a connected car, it can be a PG&E meter, it can be a utility meter, it can be your alarm systems. So for example, if any one of you were driving a Ford, GM, BMW or a Tesla and coming over to this conference, guess what? That car was always connected over a network. You may not know it, you may not have paid for it, but that device lifecycle management of the car throughout its journey back to the parking garage here was managed by either Cisco's IoT Control Center or a similar platform. So what we do is we do a full lifecycle management of that. So not only do we provide network connectivity, we also think about that we work with SPs and enterprises from the network to also provide the billing associated to that, because the car is always sending some data back into the mothership, in that case the respective enterprise motherships. So there's always some data going back and forth, hence there's usage of the network. So we have a billing associated to which is so if every account has a rate plan and a comp plan, which basically maps to how much how much they will get charged at the end of the month. Not only do we do that, we also on a daily, weekly and monthly basis, on a per account basis, we also send reports about various kinds of usage that the device is going through. And what enterprises and SPs do is they write their own engine on top of that, OnStar as an example, and essentially have their own dashboard for their use cases. The platform also has a very rich UI and an API, and there's almost a second order of business that is going on where the enterprise subcontracts it within their IT department or another contractor who will write a complete dashboard for their use case for their monitoring systems and whatnot using that API. We'll talk a little bit more about how intense that API API calls to our platform is as we go through this presentation. So before we go into a little bit technical aspect of it, let's talk about what is the ecosystem this particular platform called Cisco's IoT Control Center actually plays it. It is a market leader. How is this laid out? It's a SaaS offering. It's a multi-tenant SaaS offering operated today in private data centers, and it's basically we have 17 deployments worldwide. They are geo-replicated. So in case one of the physical data center physically goes down, we still have connectivity both from a data and control point of view. We work with about 35 plus SPs worldwide. They in turn work with 35,000 enterprises, and obviously it's impossible to list all of them, but listed you can see on the very right side flavor of the kind of enterprises we work with. Today across the 17 deployments, we have about 245 million and growing number of devices today available. Of those 245 million, about 84 million are connected car. It's one of our biggest and fastest growing business line. We are organically growing. Just with the current services, we have about 2 million devices per month. It's a 20% growth rate that we have today. And what I was talking about is the APIs. On an average, we have about 4.5 billion APIs a month call. So obviously we have to have throttling and other technologies on this platform so that nobody has a runs over or has a pseudo DOS attack because they just went through, had a much larger rate of API call than what was in the SLA. So, let us dive a little bit deeper into what the architecture of this platform is. So, I will break this up into 3 pieces. On the very right, you have devices connected over wireless network as most IoT devices connect through. We have an offering where Cisco manages the wireless network, or the customer can manage the wireless network. In the case of one of our biggest customer, we do it. So, there is a peer team next to the engineering team. This is the wireless networking team. They and the platform services work together to manage that on a 24/7 basis. We also have customers who have decided to run their own packet gateway. Part of it is their preference, part of it is because the packet gateway needs to reside closer to where the customer devices are, just because of latency. Otherwise, we will backhaul everything into where our data center is, where we host the packet gateway. So, that is called a V2 model. We in those cases write adapters which can talk to their packet gateways. So, that is the very right. The packet comes in, the whole design is done in such a way that the data and the control planes are separated. So, in case the cloud goes down for whatever reason, just by the geo redundancy design that we have, the data plane can continue to work. So, devices cannot lose connectivity. That is what our golden path is, no matter what. That is the theory at which we design at which we have. On the very top, you see customers interfacing with the platform through their API or UI. Now, when the packet comes in, basically this package is called CDRs, or call data records. Essentially, we take a copy of it, send it to the control center, and that gets pre-processed, and Alec will talk about all the details of how that gets processed. And at the end, it will be in some kind of data store, whether it is an Oracle or a Mongo or a Hadoop data store. And think about it, all the systems that we have 300 applications running in each instance of this pod. There is a pub sub model. There is a publication, and there is some applications are publishing, some applications are subscribing to those messages, consuming and doing next set of work. So, now hence comes the messaging broker. So, as you see in the very bottom, there is a messaging broker there. So far we were running with a Kestrel, which is a very legacy messaging broker, has some limitations. So, that is where we are replacing that with Pulsar. So, that is why what is relevant to this conference and the context of this deployment. We also have, along with CDRs, we also support very low end like agricultural devices and all, which only sends 1 CDR per day per month. We also have a very low end called CC Lite, where the usage is not something we have to manage on a daily basis, or well, we have to manage on, but once a day or twice a day, not on a continuous basis, as is most connected devices that you see here. So, what's the modernization proposition here? So, what we see on a daily basis is the device count and density growing up. From the customer point of view, the cost per device has to come down. Every time we renegotiate a contract, there is always this pull and push about the cost. But the customer's expectation of the experience and the service that we offer has to always move up the chain. That is really the thing. So, essentially what we are solving for is the device lifecycle management. We are seeing a continuous rapid growth of connected devices. Obviously, connected car will be the primary one. Any of the CDRs that comes into our data center, there is based on the kind of profiles we have, our comp plans, there is always an automation rule that gets triggered. So, for example, if a particular account has a usage limit, and if it moves above, we have to obviously move the rate plan and the communication plan associated to that. So, those are called automation rules. We trigger about 2 million automation rules every 2 minutes. So, that is the kind, think about it, we have 245 million devices. So, it is not much in terms of the relative numbers, but in terms of scale, that is the kind of scale we have to adhere to today, and we expect this to keep on growing. So, we have almost near real time redundant system, geo replicated. Security, because we are operating this as a SaaS, Alec will talk about it, we release every 3 weeks, but the security in the pieces associated to that has to be 100% kosher. And we need we have some clouds, depending on customers. We also need to operate them in a air gapped manner. So it's a private data center in an air gapped manner. So you essentially get, have another set of challenges that we need to work through. All of this for today's summit and relevance is the fact that we need a messaging system, which has to be reliable, which has to be scalable, extremely light overhead. What we are investing today is such that we are investing for the future. And essentially it has to be geo-replicated. Everything in that messaging system is secured, encrypted. We have to have a mechanism for rotation of passwords and keys and all of that. And it needs to work with other messaging system. Remember, we talked about a model where we talk to the customer network. That can be running on, their HLRs can be running on Kafka, and we need to talk to Kafka. So this can be other, that's extremely important. And last but not the least, it has to be recovered from any disaster. Remember, we are in a geo-replicated system. Once one data center goes down, the other picks up. But when this comes back up, everything has to sync back up. So that's the high level context and background of the platform in which we are getting into Pulsar or deploying Pulsar right now. And with that, I will hand over the rest of the presentation to Alec, who will give you a little bit of flavor of what what the technical details associated with this deployment is.
Yes, thank you, Chandra.
Yeah.
Okay, check. You hear me?
Thank you.
Yeah, so in this second part, I'm going to focus more about what we do with Pulsar, how we use it, and type of workload that we run with Pulsar, and also some information about how we deploy Pulsar and how it integrates into our CI/CD system. This first diagram here is going to show you typical applications that we use Pulsar with. And so the typical pipeline, you see a lot of records like CDRs coming into this pipeline. And the types of CDRs, they can vary based on different operators might have different formats. So they can come in CSV format or even a binary ASN.1. So this first level of ingestion is really about extracting these information and then put them in the first stage of the pipeline, which is it's a Pulsar topic there. Right? And then the next stage will more normalize this, and in our case, we use protocol buffer to normalize everything. And the choice of protocol buffer is really because of better efficiency for encoding and decoding. And it also yields a much smaller size for messages. Right? So it used to be JSON, and JSON is very slow, right, for decoding and coding. And size of messages with JSON was over 1 kilobyte, 2 kilobytes per message. And with protobuf, we could reduce this to around 400 bytes. Right? So big gain there in terms of message rate. Right? And then you have multiple stages like this. On the next stage, we'll have deduplication because we don't want to process the same CDR records twice. Right? So sometimes operators, they send multiple times the same CDRs by mistake. Right? And this is actually a pretty challenging stage because we have to keep a history of about 1 month worth of CDRs, which can amount to tens of billions of CDRs. Right? So that's a pretty intensive application there. And then the next stage will be about rating the CDR, meaning we associate a rate plan to each CDR, and then we add a lot more additional properties to the CDRs. Right? And then after that, you have additional stages to do rule automation. For example, if the usage passes a certain threshold, we have to change the rate plan. And then it ends up into a big database. So that's kind of one example of pipeline we use for. And there are multiple different pipelines, different types of messages. And what's really important for us is a streaming platform that can handle variations in loads and spikes of traffic. Right? So the traffic is kind of not very, it's kind of predictable. Right? And as you can see, you heard about having cycles like depending on the time of the day. In morning time, traffic goes up, and then evening it goes down. And even the week of the day, day of the week, on weekdays, it's a lot more busy than weekends, right? So there's variations of traffic, and it needs to absorb not only these variations, but also unexpected spikes are coming from the network, right? So, and in terms of rate, so the smaller data centers, they have maybe a few million devices, and in these cases, we have ingestion rate of around up to a few thousand messages per second, right? And on the largest data centers, they might have tens of millions of devices, and there the ingestion rate is about 10 times this, right? So about up to 10,000 events per second, right? So in terms of Pulsar, we use one Pulsar cluster to manage all these topics in these pipelines, other pipelines as well, and the sizing of this Pulsar cluster, it really depends on the expected income rate for all these messages, right? And just for reference, the smaller Pulsar cluster we deploy, they are sized to support around 50,000 messages per second aggregate, counting all the topics. And then the larger size is about 10 times this, which is about 500,000 messages per second. In terms of redundancy, so we have pairs of data centers that are always connected to each other. And we deploy one Pulsar cluster for each data center, right? And in this case, they are connected using geo-replication. So we have some of the topics are geo-replicated, and some others, in terms of retention, we do have a small retention time. Like, for example, some topics have 2-week retention, and that's used for engineering to troubleshoot. If we have problems, we can go back in time in 2 weeks, up to two weeks ago, and then replay the messages to see what happened, right? So, and we have also topics that are long-term, like multiple months. And those topics can contain a really large amount of records, tens of millions of them, right? So in terms of updates, software update, the cycle that we use is every 3 weeks. We have software updates. And applications usually update every 3 weeks. And Pulsar is the same way. We can update Pulsar every 3 weeks. And this kind of application, the incoming traffic is nonstop, right? So we don't interrupt traffic. So we have to do all the upgrades without impacting service. So that was one of the big challenges is when you have a lot of traffic coming in, you have to make sure that when you update, application restarts, you don't lose messages in this process, right? So in terms of scale, we have each of these stages can scale out individually, right? That's how we have to cope with peak of traffic, right? And Pulsar itself, we kind of dimension it to make sure that we handle the maximum load in a comfortable way, right? So we don't want to get very close to the limit there. And right now, for example, in production, we have several clusters deployed, and they are currently at about 10 to 20% capacity, right? So there's a huge room that we have to handle any spikes. And same in terms of storage, we make sure that we have sufficient storage to handle any backlogs there. The applications that we have are mostly Java applications, mostly migrating from existing code. And some of the apps are also Go clients for those that are more performance sensitive. In terms of, we talk about failovers too. So every 3 months, the applications they're running on one data center. And then the other side, they are just standby, right? So, and then every 3 months, we try to fail over all the activity to the other data center. And in terms of Pulsar, Pulsar does really run active on all sides. It's just that on the non-live side, the Pulsar is a lot less busy. It's just busy about handling geo-replication. So that's pretty much what it does there. We're going to now look at the deployment part of Pulsar, because that's something that we really spend time. About 2 years ago, we started this journey about how to deploy Pulsar in production on Kubernetes. When you get a Pulsar from open source, there's some documentation explaining how to deploy it, but there's still a lot of unknown for people who do this the first time, and for us that was certainly a big learning experience. And what we can say now is that there's really there's really 4 areas that you need to interface Pulsar deployments. They are related to storage, to the networking, to observability, and to the security. Right? So all of our deployments on Kubernetes are using Flux CD. And Flux CD is an open source continuous deployment project from CNCF. And we select this one because it was pretty easy to set up and very flexible. Right? And the way Flux works is that every cluster that you want to deploy to, you deploy a set of Flux controllers. Right? And these controllers, they will be in charge of reconciling the state of your cluster with the state that's described in the Git repository. Right? So you basically have a Git repository containing the description of all your workload. And then the Flux controllers are going to pull that repository. And then if it sees that there's a missing Helm chart or there's a Helm chart that has been updated, it will take care of triggering that update for you. And so Pulsar itself, we use the Pulsar operator to deploy Pulsar on Kubernetes. And it works pretty well with Flux because it's a declarative way to deploy your cluster. You just have a manifest file or custom resource where you describe how many bookies, brokers you want to deploy. And the operator will be responsible for creating the resources for you. And the other operator that we use, which is pretty recent, is the Pulsar resource operator. And we use this one to create other resources such as Pulsar tenants, namespaces, topics, if you need to create them ahead of time, and then also the geo-replication connections. Right? So those also work pretty well with Git-based deployment, because then you can just describe your resources in the Git repository, version them, and you don't need to write any script to have to create them, for example. Right? In terms of observability, right? So you know that Pulsar comes with options to deploy Prometheus and Grafana. Right? So in our case, we don't use these options because we have policy to send all of the logs and metrics to a central location. In our case, we send them to the cloud, and in our case, we disable the Prometheus and Grafana option. And then we make sure that all the logs and metrics from Pulsar, they go direct to the cloud. Right? So for us, it's a much better solution because we have to manage dozens of clusters. Right? And that really gives us a single pane of glass to see all of our Pulsar clusters in using one location. So that works pretty well. And in terms of observability, I think Pulsar is pretty complete, right, in terms of metrics and logs. And from that point of view, we have a lot more metrics than we can use there. Other areas is related to the storage, right? Because that will drive directly the performance of your Pulsar cluster. And in our case, we have 2 options of deployments. And the first one is based on local storage. So that will give the best performance, best latency, but at the expense of flexibility. Right? So if you have a storage drive that goes down, you lose totally the content. Right? So, and it's harder to add additional nodes because you need to procure for the hardware. Right? So better performance, but not as flexible. Right? The other option is to use network attached storage. Right? In our case, this is the easier for us because in all of our data centers, we have already NetApp storage in place. And with that, for us, it's very easy to deploy a new Pulsar cluster using NetApp data storage. And the downside of this, of course, is you're not going to have something as performant, right? But in many of our use cases, the performance numbers we get with attached storage is still good enough. In terms of security, we deploy with Istio, and Istio is the service mesh, and Pulsar operator supports Istio as an option where you can enable Istio. And this option actually doesn't really deploy Istio for you. It just helps set up the configuration of the Istio ingress gateway for accessing Pulsar behind this gateway. So it's still up to you to deploy the Istio service mesh and control plane yourself, right? And on that front, deploying Istio can be simple or very complex depending on the deployment model that you use, right? And in our case, we decided to use a simpler model where the Istio control plane is deployed in the same cluster as Pulsar, right? And we only use a single service mesh that will, where we will deploy Pulsar in it, right? And in cases where we have applications that use Pulsar that run on the same Pulsar cluster, same Kubernetes cluster, we also put these applications in the same service mesh, right? So, and that way, these apps, when they talk to Pulsar, they don't have to go through the ingress gateway, and they talk directly to the Pulsar brokers, right? And all of these communication between apps, brokers, and broker cookies, they are secure using service mesh, and they are all using MTLS in our case, right? And for external applications that need to connect to Pulsar, they have to go to the Istio ingress gateway, and we will be using TLS in that case, right? For authentication, we have decided to use JWT tokens. And so there will be a talk later today about all the security configuration of Pulsar. And so I'm not going to spend too much time there. I'm just going to say that the part of trying to design the security settings for Pulsar, that's what took us the most time. Because you need to take into account a lot of different things, like where do you store secrets, what's the public key infrastructure that you have to connect to, and then you have to also reconcile with the security policy in your organization, and then also make trade-offs based on what your ops teams can handle in terms of operations on all the keys and rotation and such. One important point for us too is being able to update Pulsar very quickly, right? So these kind of infra services used to be upgraded or updated very infrequently, right? Only when you have a bug to fix or you need a feature. But today, the upgrade cycle for these services is a lot more frequent because of security vulnerabilities, right? So Pulsar is an open source software which has a lot of libraries, right? And so it's very important to make sure that these libraries don't contain unknown security vulnerabilities, right? And that will often result in the need to update Pulsar a lot more frequently than you would need, right? And so that's a big change. And for us to achieve this pace of update, it was really important to integrate Pulsar into the way that we build and deploy any other application in our data centers, right? So the first thing that we do is that when we have a new version of Pulsar, to integrate, we import it into our Git repositories, right? And we use a tool for that. The tool will basically check all the container images that are in these Pulsar Helm charts, right? And it will copy these container images into an internal registry, right? And that way, when we deploy them, we never have to go to the internet to deploy these images, right? And the second thing that this tool does is it will modify the Helm chart so that when you deploy the Helm chart, it's going to refer to the internal version of these images and not to the external version of this image, right? And once it's imported, then the CI build kicks in, and that's where we rebuild the Helm chart. And then we put it into an internal Helm repository, and then that will be following the same workflow as any other Helm chart, any other open source Helm chart or internally developed application, right? So, and that kind of workflow that allows us to do really very frequent updates of Pulsar with minimal effort. Right? So I'm going to skip the part that describes how we manage all these different deployments. That's more like a Flux. But we have a small number of Git repositories that kind of describe the typical blueprints of deployments and how we handle the configuration for these different deployments. Learnings from these 2 years of using Pulsar, it's really from day to day having to update the Pulsar multiple times. So this combination of using Pulsar operators with something like Flux works really well for us. And that allows us to do really painless updates, right? For example, a new update of Pulsar, we can get it deployed on any clusters within half an hour by importing it. So pretty fast there. And in terms of production, we saw that for several months in production was very reliable. We had cases where we have spikes of traffic, the backlog went up, and then it recovered, the backlog was cleared pretty well. And performance-wise, the deployments based on attached storage, they were pretty good as well. Right? So areas that need improvement are more related to the scanning of Pulsar Helm charts. Right? So every new version of Pulsar brings in new versions of code. Right? And that's something that we need the community to really follow very closely and make sure that when you have a new update of a new version of Pulsar, it doesn't regress. And there's a plan to fix all the high security vulnerabilities. Other areas in production, the most important points that you have to monitor are really backlogs and resources like disk usage. Right? And for that, once you have alerts in place, it's pretty much uneventful to manage this, very low maintenance, I'd say. And the last part for updates, when you use operators, you have custom resources, and the CRDs, when they are not versioned properly from version to version, then that forces you to do certain things before and after the updates. Right? And those things that can be really, I think, improved for the next releases. And looking forward, we're looking at scaling these platforms. Right? You see the traffic will increase every month, and we're looking at scaling this and having a means to auto-scale Pulsar is really very interesting for us, because that means we don't have to continuously follow how many instances of rookies and brokers we have to deploy. Right? So something like this would be really interesting. And then in terms of apps, looking at transactions and functions, which are fairly new, and we're just waiting for these features to be more mature and then give it a try. Right? In terms of performance and Istio, so one of the issues often mentioned for Istio is that it does introduce some overhead performance. Right? So because with Service Mesh, you have a sidecar that is inserted in every pod, and then you have extra hops, right, for connectivity. And for those, there's a new version of Istio that came up recently that provides the same mesh without the overhead of a sidecar. So this is something I think that we will be trying soon on Pulsar. And configuration management is also a challenge. I think any continuous deployment system you use, that will be the most complex part. Like how do you manage complex configuration when you have a lot of clusters and different types of deployments. Yeah. I think that's pretty much it. And so if you have questions, we can take a few questions.